Since we're dealing with equations that have exponents in them, we're going to have to talk a little bit about log functions and the properties of log functions. There's really only one thing that we need to worry about, and that is the log of y to the x is the same as x times the log of y. That's really the only algebra property that we need to know about. So as an example of this, if I write the log of 5 to the 10, that's the same as writing 10 times log 5. What else do we need to know? Well, we need to know what this is equal to. And fortunately, most of our calculators have a button that says log on it. So if I look for that on my calculator, pressing log 5 and enter gives me the number 0.69897 and so on. And then I can multiply by 10 and I'm left with 6.9897 and so on. So let's look at an interest problem where we need to use this. This is example 7 on page 403. Dee has invested $8,500 in old Star Wars memorabilia, which is currently increasing in value at 6.5% per year. If this increase continues at the same rate, in how many years will Dee's investment double? So if we read it again, we'll see that the present value, or the principal invested, is $8,500. It says that it is compounding at a rate of 6.5% annually, or 0.065 as a decimal. Also, it says n is 1. It says compounding once per year. And then the accumulated amount, we want our investment here to double, so doubling 8,500 is 17,000. The thing that we're missing in this problem is the time it takes in order to double. So if we put our equation together in our compound interest equation, we have 17,000 is equal to 8,500 times 1 plus 0.065 divided by 1 to the 1 times t. In this problem, the thing we're looking for is in the exponent, and we need to use the log property to be able to bring it out of the exponent. Before we can do that, I really want just the thing with the exponent on its side by itself. So we'll do a little bit of algebra here first before we can use the log. So we have 17,000 is equal to 8,500 times 1 plus 0.065 divided by 1 is 1.065, and 1 times t is just t. Since I want to isolate this part, that means I want to divide both sides by 8,500. So if I take 17,000 and divide it by 8,500, what do I get? Well, you should get 2, because we calculated the 1,700 by doubling 8,500. 17,000 by the 8,500. So we're left with this. Okay, this is the part where we need to use the log. There's a property in algebra which says I can take the log of both sides that is what we're going to do is we're going to write the log of 2 is equal to the log of 1.065 to the t. And now I can use that power property to bring this power out front. So the log of 2 is equal to t times the log of 1.065. Typing some things into our calculator, we get the log of 2 equals 0.30102 and a bunch more decimal places. The log of 1.065 is 0.027349 and a bunch of decimal places. So we want to get this over to the other side, and since it's connected to the t by multiplication, we're going to have to divide both sides by that number. So we'll take that 0.30102 divided by 0.027349, and what we get is 11.0067 and more decimal places equals t, which to me looks a lot like 11 years. What that means is that it's going to take 11 years for our investment to double. There's a rule that comes up because of all these log rules and doubling, and this is a pretty common thing. And the rule for doubling time is take 72 and divide it by the growth rate. And that'll give us an approximate doubling time. So in this problem, this last problem, our growth rate was 6.5%. So what we can do to get an estimate, and this will be close enough for what we want to do, is take 72 and divide it by 6.5. Notice this is 6.5, not 0.065. And when we do that, we get 11.6, which for our purposes is close enough.